Have you ever seen one of those wild headlines about a new study and just thought, can I actually trust this? Well, today we're opening up the detective's toolkit. We're going to break down how you can become a much smarter consumer of all the science news that's flying around so you can spot a questionable study from a mile away.
Yeah, you see headlines like this all the time, right? Coffee cures aging. They're exciting, for sure. They get a ton of clicks, but they often leave out the most important details. So the real question is, how do we look past that clickbait and actually judge the research for ourselves? How do we know if that coffee study is the real deal or, just a bunch of nonsense? That is exactly what we're going to figure out. So, to be a good research detective, we really need to get a handle on one key concept, and that is validity. Now, validity sounds kind of academic, but all it really means is truthfulness. Is what the study claims it found actually true? And that truthfulness, it turns out, comes in two main flavors. Think of it like this. First, we have internal validity. This asks a really simple question. Was the experiment itself done right? Can we trust the results from inside that controlled lab setting? And then we've got external validity, which asks the other crucial question. Okay, so the experiment was perfect, but do these results actually matter out here in the messy real world? Can we apply them to you and me? Let's tackle internal validity first. All right, let's put on our lab coats, metaphorically speaking, and step inside the experiment itself. We're going to be looking for threats to internal validity, those little clues that something went wrong during the study that could make the whole conclusion fall apart. Our first big suspect is called selection bias. This is the classic flaw. It basically means the groups you're comparing weren't equal to begin with. And if one group is already different in some really important way, how on earth can you say your treatment is what caused the final outcome? You just can't. Check out this perfect example. Picture a study on a new program to help people quit smoking. Now, if you compare people who volunteered for the program to a group of people who refused to join, well, you're not really comparing the program's effectiveness, are you? You're basically just comparing motivated people to unmotivated people. The volunteers were probably more likely to succeed no matter what. That is selection bias in a nutshell. Okay, next up, we have a threat called history. This is what happens when the real world just crashes into the middle of your perfectly controlled experiment. Some big event happens that has nothing to do with what you're studying, but it ends up messing with your results anyway. So, for example, imagine you're running a class on prenatal training, and right in the middle of it, a huge, scary news story breaks about rising maternal complications. Suddenly, interest in your class skyrockets. But was it your amazing class, or was it this external event, this history factor, that got everyone's attention? It's impossible to know for sure. This next one is a little more straightforward. It's called instrumentation change, and it's all about the tools you're using to measure things. If your scale or your blood pressure monitor or even the survey you're using changes or breaks halfway through the study, well, then your before and after measurements just aren't comparable anymore. The data's junk. So let's test this out. Think about this scenario. In the middle of a big clinical trial, some of the dialysis machines break down. What kind of threat is that? Well, it's not about the people. It's about the equipment, right? This is a textbook case of instrumentation change. And the last internal threat we'll look at is mortality. Now, this sounds dramatic, but in research, it usually doesn't mean people are literally dying. It just means they're dropping out of the study. And this becomes a huge problem if more people drop out of one group than the other, because it can seriously mess up the average results of the people who are left. For instance, let's say people in the group getting the new treatment start dropping out because they can't get a ride to the clinic. So who are you left with? Probably only the most motivated, or maybe the wealthiest participants who can afford transportation. Your sample is now totally biased, and this difference in who drops out is exactly what we call mortality. Okay, we've officially investigated the crime scene inside the lab. But here's the thing. Even if an experiment is perfectly designed on the inside, we still have to ask that other big question. Do the results actually apply to the complicated real world? These are the threats to external validity. First up is a huge one, and you may have heard of it, the Hawthorne effect. This is a fascinating quirk of human psychology. It's the idea that when people know they're part of a study, when they know someone's watching them, they often change their behavior. Maybe they try harder, or they're more honest. They just don't act like they normally would. So, what happens when a researcher just comes right out and tells people they're being observed? Well, they're pretty much inviting the Hawthorne effect to the party. The very act of watching changes the behavior that you're trying to watch. It's a real paradox for researchers. Now, this next one isn't about the participant, it's about the researchers themselves. It's called the halo effect. This is a type of bias where a researcher's first impression of a participant, whether it's good or bad, can totally color their judgment and influence how they rate that person's performance. Imagine a teacher who knows a particular student is on the dean's list. Without even really testing them, the teacher just assumes, oh, they're a great student, and gives them a high score. That positive halo from being on the dean's list unfairly influences the assessment. The scary part here is that the researcher's bias, not the subject's actual skill, is creating the result. So you might be thinking, wow, with all of these potential flaws and biases, how does anyone ever conduct a study we can trust? Well, that's a great question, and the good news is smart researchers have developed methods to fight back against these threats. The first line of defense is what's called a blind experiment. The logic here is pretty simple. If the subjects don't know whether they're getting the real medicine or just a sugar pill, what's called a placebo, they're way less likely to change their behavior just because they think they should be feeling better. This is a direct counterattack on the Hawthorne effect. But we can take this a huge step further to what is often called the gold standard of research design, and that is the double-blind study. In this setup, two different groups are kept in the dark. First, the patient has no idea if they're getting the real treatment or the placebo, and second, and this is key, the doctor or researcher observing them also doesn't know. This is so powerful because it helps eliminate both the Hawthorne effect in the patient and the halo effect in the researcher. So, just to lock this in, when you have a study where neither the doctor nor the patient knows who's getting the new drug, what do we call that? That's right, it's a double-blind study. It's really the best tool we have to make sure the results are as objective as humanly possible. All right, let's pull all this together. Here's a quick summary of the common threats we've been talking about. We looked at the internal threats, the things that can go wrong inside the lab, like selection bias, history, broken instruments, and mortality. And then we looked at the external threats, the real-world problems, like the Hawthorne effect and the halo effect. Just being able to spot these is a huge step. So what's the big takeaway here? It's that you now have a powerful toolkit. The next time you see a flashy headline, you don't have to just accept it. You can start asking these critical questions. Think like a detective. Ask about how the subjects were chosen. Ask if people dropped out. This is how you go from being a passive consumer of information to an active, critical thinker.
And that brings us to a final thought for you to chew on. Now that you have these tools, what's a common fact or a widely held belief you've always heard that might just be built on a study with a shaky foundation? Start looking around. Keep asking questions, because that right there is the heart of all good science.